In this part, we're going to look at Theorem 2.6, which deals with limits at infinity and powers of polynomials. So, before I even get started, I want to go over just two very basic polynomial functions that we should all know their graphs. So the first one is going to be the polynomial f of x equals x squared. And the second is going to be f of x equals x to the third, because those two are going to help us out with learning all four of these properties in this theorem here. So the first, we got to be able to identify that we have a polynomial. So p of x equals an x to the n plus an minus 1 times x to the n minus 1 and so forth, all the way down to a2x squared plus a1x plus a0, where a sub n does not equal 1, is going to be a polynomial. Then we have these four properties. The first one says that as long as the limit as x approaches positive or negative infinity of x to the n, and here's the key. Let me get out my highlighter here. Where n is positive, this will always go to infinity. That is right here. F of x equals x squared. So if you have x to the fourth or x to the sixth, x to the eighth, and so forth, as long as that exponent is even, you already know what the end behavior of your graph is going to look like here. And what I mean by end behavior is as x goes to infinity or as x goes to a negative infinity, what do the outputs look like? And in this case, they both go to positive infinity. Now, in the second situation, you have the limit of as x goes to infinity of x to the n is going to equal positive infinity, which is right here. So I just highlighted that in green. Or, let me use yellow here, or negative infinity if the limit as x goes to negative infinity. So in this situation, you got to be careful, because when n is odd, like x to the third, you have the shape of our function on the right hand side. So if x goes to infinity, it goes to positive infinity. And if x goes to negative infinity, then the function is going to go to negative infinity. For number three is just an extension of the negative exponent rule. In other words, the limit as x goes to positive or negative infinity of 1 over x to the n. Another way to say that is the limit as x goes to infinity, plus or minus infinity of x to the negative n equals 0. So what we're really saying here is this. For example, if we had the limit as x goes to infinity of x to the negative 2, well, I can rewrite that as the limit as x goes to positive infinity of 1 over x to the second. And here's what's happening. Basically, if you think about substituting in the limit, you have 1 divided by an extremely large number. All right, I'm going to erase these functions on the right-hand side because I'm going to write over here. So when you have 1 divided by an extremely large number, that is essentially 0. An easy way to think about this, just think about 1 divided by 10, that's 0.1. Then 1 divided by 100, well, that's 0.01. 1 divided by 1,000 is 0.001. So notice that the larger the denominator gets, the smaller your output value gets, or the smaller that your limit's going to get. And that's just going to be 1 divided by infinity is essentially 0, because it's 1 divided by a huge number, okay? Then the fourth property deals with the leading coefficient in the leading term. So what this says is if you have the limit as x goes to positive or negative infinity of p of x, which is a polynomial, all you're really going to focus on, and let me highlight this, I'm going to use this magenta one, is you're going to focus on this term, which is the leading term in our general polynomial. So depending upon the degree of the polynomial and the sign of the leading coefficient, you're going to know if this goes to positive or negative infinity. So let's look at some examples we have here. For the first example, there's my leading coefficient. Since it's even and 4 is positive, I'm going to go to positive infinity. For the second example here, here's my leading coefficient. Since the degree is even and this is positive, even though we're going to negative infinity as the limit as x goes to negative infinity, even though that's going to negative infinity, my leading term tells me it's going to go to positive infinity, okay? If you don't believe me, just graph it. The graph is going to look just like this because n is even. The degree on the polynomial is even, so I know that's what it looks like. Now, for the next two examples, the limit as x approaches infinity, well, here's my leading coefficient, or my leading term. Since that is odd, I got to be careful. Since I'm going to positive infinity, I know this will go to positive infinity. However, with the last example, as the limit of x approaches negative infinity of 5x to the third minus x squared plus x plus 15, this is my leading coefficient, my leading term. Since that is odd and that my limit is going to negative infinity, this is going to go to negative infinity as well. And you got to remember that's what the graph looks like. Okay? Now, the next example I'm going to do is we're just going to evaluate some limits here. Just evaluate some limits. And we're going to we got to think about what's happening. So with this first example, the limit as theta goes to infinity of cosine theta over x squared, or I'm sorry, theta squared. Let's think about what's really happening here. So if I think about cosine theta, here's what I know about cosine theta. The graph is going to be bounded in between -1 and 1. And it just oscillates, okay? So no matter what, the max this graph will get is 1, and the minimum this is going to get is 1, or -1. The question becomes, that theta squared, what is that doing to my function here, all right? So if we think about this, notice we're kind of just setting up, just by understanding what cosine theta is, we're setting up the squeeze theorem here. So I'm going to divide everything by theta squared. And then using the properties above, I'm going to think about, okay, well, what's really happening here? 1 over theta squared, okay, is the same exact thing as saying, I'm going to write it over here to the right. I'm going to write it in this box. See, I'm drawing this box on the right-hand side. Sometimes if we write it out just using the variable x, it makes a lot more sense. 1 over x squared goes to 0 as x gets larger and larger and larger, okay? On the other side, -1 over x squared also goes to 0. See, that's going to be, I'm going to scroll up real quick. That's right here. Property number 3. That's exactly what that's saying, okay? So if you think about this, if the left side goes to 0 and the right side goes to 0, then by the squeeze theorem, so let me write this out real quick. So the limit as theta goes to infinity of cosine theta over theta squared has to equal 0 by the squeeze theorem. Now, to convince you, we're going to go ahead and graph this. We're going to see what happens here. So I'm going to pull up Desmos. All right, so I'll do the left side first, which is going to be -1 over, and I'm going to use x squared. Okay. Now, +1 over x squared. Okay. And now I'm going to do cosine. So let me get a fraction here. Cosine of x over, and watch what happens when I type in x squared. Let me screw over here a little bit so you can see what's happening. Because remember, we're concerned with as x or as theta goes to 0. I mean, goes to infinity. So let me go ahead. Let me change this up here a little bit. So we're going to make x go from, let's say, -1 to 10, just so we could see it. And then y, I'm going to make y go from -0.5 to +0.5. All right. So let's get this back here. So in red is -1 over x squared. In blue is 1 over x squared. Those are the outsides of my squeeze theorem. And then green, which is cosine x over x squared, is going to be the middle part. And as you can see here, as we let x go to infinity, this just squeezes it down. It just squeezes it down. So I think the squeeze theorem is just, honestly, it's one of the coolest theorems that we can use to help us to determine what's happening in terms of limits and stuff like that. Okay? Now for the last example, I think I have one more example here. Let me zoom in. There we go. So the last example is the limit as x approaches infinity of 3x squared plus, or I'm sorry, 3x to the 12th minus 9x to the 7th. Here's what's happening here. We have a polynomial. That's my leading term. I'm going to be honest with you. I don't even care about this. At the end of the day, that minus, what was it again? Minus 9x to the 7th. It's not going to do anything because my leading term is going to determine, like I said, the end behavior. It's going to let me know what's happening here. So, since the 12 is even, that's positive. As x goes to infinity, this limit will go to infinity as well. I hope that helps. Now, the next example that we're going to look at, we're going to deal with what we call rational expressions or rational functions. Okay? So I'll see you in the next part.